Okay, 1.9 is on nested quantifiers. Okay. If a predicate has more than one variable, each variable must be bound by a separate quantifier. Okay, if there's more than one quantifier. Such a logical expression is said to have nested quantifiers. So we could have for all x, for all y, p of x, y, we could have for there exists an x and there exists a y such that p of x, y. We could have there exists a y for all x, p of x, y, or for all x, sorry, this is the way around. There exists an x for all y, and for all x there exists a y, p of x. Example 1. Okay, let m of x, y be x sent an email to y. So, okay, for all x, for all y, m of x, y, okay, if and only if, okay, everyone sent an email to everyone, okay, right? So everyone sent an email to everyone. Does that include the person sending the email? Yes or no?
Yes.
Everyone sent an email to everyone. So was that Bob?
That was me, but I'm thinking
Oh.
yes, because they fall within the domain.
Right, exactly. So if you are in an office building and you send an email to everyone, it includes yourself, right? So you would like reply all to a corporate, group, right? And you are actually, if you're in that corporate group, then you're gonna get the email back as well. Right, does that make sense? Okay, so everyone send an email to everyone. That includes yourself. Okay. Okay, what does this one represent? There exists an X and there exists a Y such that M of X, Y, okay, implies that someone sent someone an email, right? There exists X who sent at Y an email. Okay, so there is a person who sent an email to someone. We don't know who these people are, but some X sent some Y an email. Okay. Okay. What would be the logical equivalent of this statement? Somebody help me out with that one.
Would it be someone sent an email to everyone?
Absolutely. Thank you, Lukesh. Okay, someone sent an email to everyone. Right? Someone sent an email to everyone. Okay? And then what about the last one here? This one should be what? Well, everyone sent an email to someone. Okay, and that could just be them sending an email to themselves. Everybody sent an email to themselves, so that's fine, right? But you know, or they could have all sent it to the same person. But that doesn't, but that's not specified here. It just says everyone emailed someone. Okay. Okay. Example 2. The domain of X and Y are all non-negative integers. Okay, all non-negative integers. Find the truth value of the following statements. Okay. Okay. A. For all X and all Y, X times Y equals 1. For all X and all Y, X times Y equals 1. Is that true? It is false. Can you give me a counter example? Sure, just give me two positive integers. Okay, or you could even give me zeros. I mean, anything, right? We could say let x equal 2, y equal 3, and x times y is 6. So counterexample. You can come up with any counterexample. Okay, so this is false. Okay, B. Okay, there exists an x and there exists a y such that x times y equals 1. Is this true or false? There exists an x, there exists a y for which x times y equals 1. Sure. Okay, can you give me the example? What's the example? Yep, thank you. X equals 1, y equals 1. Okay, perfect. Okay. Let's talk about alternating nested quantifiers. Okay, alternating nested quantifiers. Quantifiers are applied from left to right. Okay, quantifiers are applied from left to right. Okay. So, for example, for all x and y, p of x, y, okay, okay, one variable sets the existential bound, or I'll say the universal bound, and one sets, oh, I'm sorry, this should be, okay, so sets the existential bound. Okay, one sets the universal bound and one sets the existential bound. So it could go for all x, there exists y, or like we saw above, there exists an x for all y, p of x. Regular. Okay, example 3. Okay, given the domain of x and y is the set of all integers find the value of A. Okay, for all x, there exists y such that x plus y equals 0. Okay, so is that true or false? For all x, there is a y such that x plus y equals 0. If it's just the set of all integers, not necessarily the set of all positive integers. It's just the set of integers. So if you give me an x, okay, so this is true, let y equal negative x, right? You give me an x, I can take its opposite, right? I can take its opposite and let that equal y, okay, thus x plus negative x will always equal 0. Okay. Okay, what about the other way around? There exists an x such that for all y, x plus y equals 0. So we have to think of this in terms of going left to right. Okay, this, you kind of have to think of it as, okay, we first choose the for all x, and then we choose there exists a y, right? Okay, let's think about that for a second. First, we choose the domain for all x, and then we have to match that up with a y, right? So for all x, all of these x values, okay, have to pair to a y value, right? And we just say, yeah, just let negative x pair that up. So we're saying all x, there exists a y such that, but once again, it's left to right. We start with the x and we go to the y. Right? What happens if we reverse it? So there is an x, there exists an x such that for all y, I get 0. Does that work? If I give you an x, or is there an x that will get me any y to be 0? Does there exist an x such that when I add it to y, or add it to any y, it will get me 0? And the answer is no. It doesn't exist. Okay, there is no value of x that when I add it to y would give me 0. Now, this would be true if it was multiplication, right? If it was multiplication, then I would just say, oh yeah, just let x be 0. And that would always get me 0. But in this case, there is one, because it's addition, there is no way to pick a value of x that will always get me when added to any y. Okay, so we can kind of think of these as, in a way, nested. Okay, in parentheses, like for all x, for all x, there exists a y such that x plus y equals 0. Or there exists an x that works for every y. So this is false. Okay, no integer exists that when added to y, that once chosen, will sum to 0. Okay, De Morgan's law. Laws for nested quantifiers. Okay, De Morgan's law for nested quantifiers. Okay. Oops. Okay, not all x, all y, p of x, okay, is logically equivalent, okay? So I'm gonna bring this inside, right? I'm gonna bring this inside. What happens when I bring a negation inside? It changes the it changes the quantifier from universal to existential. Does that make sense? So the intermediary step would be to take this guy and go like that. And we would say, well, now it becomes existential. Right? So kind of think of this as, leapfrogging. And every time you leapfrog, it changes from universal to existential or vice versa. So we're going to leapfrog this negation and it's going to change this here. Well, let's do it one more time. Well, this is p of xy. Sorry. Let's do it one more time. So then it's just going to become there exists x, there exists y for p of xy. Right? If I do the same thing, but they're existential quantifiers, you could see, okay, we're going to leapfrog that one. That becomes a universal. Negate the y, existential. Negate the existential y. P of xy, and we get for all x for all y, p of xy. Okay. What if we wanted to negate for there exists an x for all y? Then once again we're going to leapfrog, And we get that guy. Do it one more time. And we get, oh, sorry, this should be for all. Okay, this should be for all. For all x, there exists y. P of x, y. And then for all x, there exists y. P of x, y is going to give me there exists x. There exists y. Negation of there exists y. P of x, y is equal to there exists x for all y. P of x, y. Okay. Okay, so let's write this up kind of nicer. The negation of alls negation of for alls is there exists. The negation of there exists is for alls. Okay, the negation of there exists x for all y is the opposite. There exists x, there exists y. And the negation of for all y, well, no, for all x, there exists y is the opposite as well. This is there exists x for all y, p of x, y. Okay, so that's De Morgan's rule, laws for nested qualifiers. Nested qualifiers. Okay, lots of De Morgan's laws. I think we have 4 so far. Okay. When we move into chapters 2 and 3, we'll end up with, I think, 2 more. 2 or 3 more. So a lot of De Morgan's laws. Okay. Okay, example 4. Okay, let the domain be students at a school. Okay, LXY implies that X likes Y. Okay, X likes Y. Okay, so what does this mean? Okay, the negation of X for all Y, okay, of L of XY. We want to negate this thing here. Okay.
Professor, sorry, I think there are a couple questions in the chat.
Oh, sorry.
I think some people asked some questions.
Isn't there supposed to be a negation in front of P of X? Oh, yes, thank you. There is. Is it supposed to be? Yes, there is. There is supposed to be negations. Yes, sorry about that. Okay. Because we could have carried that through, right? Is that? No, I don't think so. Honestly, I don't think so. Let me just make sure. I'm pretty sure that the opposite of for alls is, you know, not for all is, because I don't think we're carrying it. I'm not sure. Let me see. Pretty sure that that's not the case. Oh, you're right. It is for not. Okay, thank you. Yeah, I forgot the knots. Thank you so much. Okay, so it is not P of X. I don't know why I wrote it wrong in my notes. Okay, perfect. Thank you so much. Okay. Sure. Fix them. Okay, perfect. Okay. So let me go back to zoomies. Okay. Okay. Okay, so what does this mean? Okay, what does this imply? This implies that there is no student, okay? It's actually not like, it's not in parentheses. It's just saying, look, there is no student who likes everyone at the school. The negation is only getting applied to the first quantifier. Okay, the first quantifier. Okay, the negation only gets applied. Okay. So there is no one who likes everyone at the school. Okay? There is no student who likes everyone at the school. That's what that means. Okay, let's apply De Morgan's law to this. Okay, so as we leapfrog, they're going to shift. For all x, there exists y such that not L of x, y. Okay. What does that mean? That means that all students have someone they what? All students have someone they do not like. Okay, yes, makes perfect sense. Okay, so I just, for whatever reason, I left off the negations. Okay, thank you for that correction. Okay? These two statements are logically equivalent. They're logically equivalent.